Hello and welcome to my video 2, or this is going to be video 4B on the modern GL, a little bit of a show and tell about what I've been up to. And one thing I forgot to do in the last video is I was going to show some of the simple mistakes I made and some of the weird results that weren't immediately intuitive as to what was going on. And I'm going to go ahead and run the debugger here. And turn on the console. I'm going to go ahead and run the code. And you'll notice this guy is null. And I don't think it put anything... here we go. Yeah, and so the callback said error invalid OpenGL version 00. And you can see why that happened. I accidentally misspelled this. So that's why the error callback can be very helpful. So let's go ahead and fix that one. And stop it. And run it again. So, but that guy just went along on its happy, merry little way. So in this case, error logging is a very important thing when you're working with OpenGL. So now it has version 4.0, it's happy, it's created the window. And you notice that I commented out glue. Now I've said in a previous video, glue's job is to associate the function pointers of the OpenGL, I'm going to call it the client side, the CPU side, and link those to the API and in the drivers and on the graphics card. So that's on the manufacturer side, because different cards, different manufacturers, those functions bodies are actually going to reside in different places. So glue is going to do the correct association. So right now I've disabled glue. Okay, so now we're going to go ahead and run it. And go ahead and jump to our sorry, I already had a copy running. Alright, so step into and step over, run to this line right here. Alright, so now this is one of the OpenGL commands, so if we try and run it, it gets a null access. That's because glue has not actually associated this function with a valid address in the API. So if you ever come across this problem, first thing you do is make sure your glue initialized correctly. So go ahead and stop it. Go ahead and run it. Let's try that again. And step over. So I'm going to go ahead, since I know it's going to work. So that's right now set to 0. So now it's been given name 1 and associate the things, the attribute pointers, and it returns the VAO value. So I'm going to go ahead and kill these and step out. Kill all the breakpoints. So if we look at this array, you can see, so you can see this is Vertex Array Object 1, there's 310 points, Vertex Array 2, 287 points, and Vertex Array 3, 353 points. Now it is important to keep track of the number of vertices in these objects. Or at least I think it is. It's a little odd to me that the vertex array object can hold all that information and you can't at some point specify how many points are actually in the buffer. So I very well could be doing it wrong. If somebody else thinks that this is incorrect and knows the answer, I would be ever so grateful if you'd leave a comment and tell me that one. Until then, I will keep looking into it. So now we've got our buffer data bound. So we need to get our shaders ready and compiled. So I'm going to go ahead, and I'm going to go ahead and start by writing the shaders. Now, I've noticed a lot of people like to write the shaders as a collection of strings. I like to write it all out at once as a raw string. Now, the reason we actually write the shader code into a string so we can pass it to a buffer to be compiled. And part of the reason for this is different graphics cards may compile this code differently. Different manufacturers may compile this code differently. So that is why it is compiled at runtime. And that is also why it is very difficult sometimes to, there's no way you're going to get a compile time error. So if you make little mistakes, then you can be shot in the foot. Very important to put in error logging for this. So I'm going to go ahead and put these in here so that we can associate them with the attributes we set up earlier for the we set up for the vertex array object. So notice that we got this in specifies that this variable is an input, and that the layout location is 0, and it is a vector 2. So this is an ANSI C-like language in its syntax, but it is not ANSI C. So notice, so we got a vector 2 and a vector 3. So that is matching up with how we've told the graphics card to interpret the buffer data. So what's going to happen is when the code is actually run, the first 2 bytes, or pardon me, the first 2 floats of the buffer are going to be pushed into this vector 2 right here called position, and these 3 floats are going to be pushed into the second location, or the second location, vector 3. So this is going to hold our x and y value for this point, and this is going to hold our RGB or BGR value for this point. And one of the wonderful things about how this works is there's going to be an instance of this shader generated for every 5 floats. So for every point we're going to get a separate shader, and these shaders are going to be run concurrently across the multiple cores of the GPU. Well, I say concurrently. Assuming that the cores are available, they will be run concurrently. So this means that this is going to be pretty quick. The bad thing is these shaders can't talk to each other across cores. They can share memory locations. That's about it. So when you pass data to these guys, expect that all the data has to be pretty much self-contained unless it's what's called a uniform. And actually, let me go ahead and do this. So I'm going to get to this one in just a second. And I'm going to talk about this one real quickly. So this uniform indicates that this is a common memory location, so that this variable is going to be it's going to be the same, it's going to be uniform across every instance of this shader. So, and this guy's actually going to hold our matrix information that normally would have been handled in the old style by the model matrix or the perspective matrix. We have to pass this guy in ourselves, and you're going to see that when we get to the rendering portion. But the big takeaway is uniform means that, think of it as a static variable. So this is going to be a common memory location. It's going to be the same value across all of them. This doesn't necessarily have to be the matrix, you can pass in anything you want. You can pass in arrays that maybe are the different light sources for the scene, so that the shaders can respond to different aspects such as that. So when I finally grasped how that worked, I just thought that was the coolest thing since sliced bread. Okay, so now when the shader runs, we've got our position right here, we have our color right here. Now the Vertex Shader is going to run an operation, one for each vertex. So, and what we're going to get is I believe we're going to get a 2D raster location for where it's going to be put to the screen. So we're going to multiply our matrix math. So this actually stands for model, view, and perspective. So this is 3 matrices that are multiplied together, and then we multiply them by our 2D point here. Now there's a problem with that because this is a 4-dimensional vector, and I highly recommend, if you haven't already, look into how matrix math works. It is really useful to understand for 3D graphics. So we need, but just trust me, you need this to be a 4-element vector in order to be able to multiply it by a 4x4 vector. So the cool thing is you can define a 4vec right here, and then put in the extra elements here. So right now it's going to do the X, the Y, the Z, and this, I actually forgot what this is, and I feel bad because I took a class on this, and the teacher was an absolutely wonderful teacher. So Dr. Peng, I'm sorry if you ever see this. I know that this specifies that this is a point and not a vertex. This has to do with affine transformations, and this needs to be 1. It's absolutely essential. So out of this operation, we're going to get a final raster screen location, and it is pushed out through this special variable. There is actually a list of special variables for the different shaders, and there are a couple. There are a couple more. We're only going to work with the vertex and the fragment, but the geometry shaders one I've been very interested in of late, but for another video. All right, so we have our 2D point, and we don't do anything with color here. That's the job of the fragment shader. So we're going to go ahead and we're going to pass along the color that was received from the buffer and just pass it straight along, and it's going to send to the fragment shader. So this becomes a pass-through variable. So the big deal is this is out. It's a 3 vector because we got our BGR value, and this is just the name. So now that we have that, and that's all there is to our vertex shader. So if you think of the fixed pipe shader, the one where you have to set all the various states, I imagine that that one was probably much bigger. So in writing our own vertex shader, this is probably much smaller, much more efficient, and gives us a lot more control. Alright, so I'm going to go ahead and move on to the fragment shader. And I love raw strings. As I said, most other people I've seen do this with multiple strings and then just append them together. And I think that some of the tutorials I was probably looking at were older. I think raw strings were introduced with the C++ 14 standard. So anyway. Alright, so we're going to have a single output from this guy, and he's going to be a vec4, and that is just going to be the out color. So it's just understood inherently, this one doesn't have a special name, that this is the one output from the fragment shader, and this is the color that is going to be applied to the fragment associated with the output of the Vertex Shader. Now, I'm going to say this right now, I'll probably repeat myself later, but part of the reason I like doing this point by point as a demonstration, you'll notice that a lot of the other guys doing their tutorials use triangles, and they do the colorful thing like I did with the square in my last, or video 3, I'm going to say. And I mean, that's great, but what I like about this is you get a one-to-one relationship between the Vertex Shader and the Fragment Shader. With the Triangle Shader, what's going to happen is the Vertex Shader is going to be run 3 times, once on each point, and then somewhere in between the Vertex and the Fragment Shader, there's going to be multiple fragments generated in between all the vertexes of the triangle. So this way, like I said, you got a one-to-one relationship. For every vertex shader you've got, you're going to get one fragment shader. So you're passing this color along, it's going to go directly to a corresponding fragment shader. I don't know if that makes it any easier, but it just made it easier for me to understand. So we're going to be getting our input vec3, and it's important that these be the same name between here and here. So that's how it links these guys. So as I said, this is a pass-through, comes in the vertex shader, goes out to the fragment shader, and then the fragment shader is going to go ahead and bind that color to the corresponding point. Alright, so yeah. Alright. So we are setting our out color, and we are going to set it same thing with what we did up here. This is wants a vector 4, but we got a vector 3. So we're going to go ahead and put the vector 3 here. So the BGR values are going to be associated to the first 3 elements of this vector. And this last guy is going to be our alpha, which is important in blending. So 1.0 means that these colors are going to be full strength on that point. There's no kind of transparency there. Now, I haven't actually experimented with this yet. I've done some work, and I tried putting other values in here, and it didn't seem to make any kind of difference. But for this, we're just going to call this 1, and I'm going to continue working, and when I find a solution to that, I will probably make another video. So, moving on. Alright, so now we have our shaders, and we need to compile these and link these on the card. So I'm going to go ahead and add another function here. Call it compile shaders. And this code is pretty straightforward, doesn't change very much. So if you were writing your own objects to handle this stuff, it probably could be consolidated pretty easy. I'm actually trying to do some experimentation with that myself. But alright, so like most other OpenGL things, we give these guys integer names. And so we tell the card we're creating a new vertex shader. And a new fragment shader. So that's going to give us 2 integer values that we can use. Alright, now the commands coming hereafter want arrays. I assume that's so that you can handle things unbatch, but we are only doing one of each, so we're just going to create this single element array so that we can populate it to pass it to the compile command. So we're going to go ahead and say shader, and that guy is going to be equal to this. There's probably an easier way to do that that doesn't involve that in between, but it's a small thing, so I'm not worried too much about it. So we tell it which one we're associating it with, and we're giving it the source string. And I'll be honest, I forgot what that 0 does, but this is saying, so the Vertex Shader ID, we've got one element in this array, and that will load the code in here. And then we go ahead and we ask the card to compile our code. And in the first iteration of my video, I didn't bother to put, I actually am embarrassed to say I said checking a log was outside the scope of the video, and one of the reasons I've redone it is because there were issues, because it is so easy to mess that up. So I've learned my lesson. We need to put in logging. So this command right here, it's GL get shader, and that means for. And in Jamie King's video, he explained why that was, and it's kind of a historical thing, and I can't quite remember what it was, but this is holding to an old convention from the beginning of OpenGL. So, alright, so we've just said we want the compile status. So this is integer is going to represent that. So we test that integer. So if the GL compile is not true, so if it failed to compile, we go ahead and we say, we put a little bit of output. Alright, and we are going to want to create a variable, because we can't just ask for the text description. First we have to say, hey, how big is that buffer? And then we have to create the buffer, and then we can populate it. And I kind of remember a lot of old NCC APIs working similarly. Alright, and I personally, for this kind of thing, like to use unique pointers. If you're not familiar with them, I highly recommend going and looking into them. This is a managed pointer type, so that you can create a variable size buffer, and it will be self-deleting within the scope of this condition. So you do not have to worry about managing that resource. C++ 11 really introduced a lot of wonderful helper objects for managing resources. So, alright, so now we're telling it we want the log from the Vertex Shader, and we're going to say, actually let me just do this, and we already know how long it is, so this is pretty much saying how long the buffer we've created is, and this tells us how many bytes were actually sent. We don't have to worry because we've already dynamically created one that was the perfect size. And I'm going to static cast it, and the nice thing about a unique pointer is it is easy cast it to that array. So that is going to populate our dynamically generated array, and we can go ahead and pump it out to our debug output. Alright, I'm going to go ahead and actually I just realized I've been doing all of this in the debug context. Go ahead and build it. Did I leave? I did. Alright. I had an instance running, and so it's not going to let me have access to the exe. Alright, so I'm going to get a little ahead here. And I am a copy pasta person. Alright, so we don't want any breakpoints in there. And right now we're just going to return 0, so I just want to give a little demonstration here about how this thing can sometimes be a little wonky. Alright, so we're going to go ahead, run it down. Alright, so now we're going to go into our shader compiler. So we loaded the code, we've compiled it, and it's 0, and I believe that means it's true. Nope, it failed, which is sad because I wasn't planning it on failing it here. So, but let's go ahead and see what the, let's see, unknown. So you can see it's given us a nice clear error. Sometimes all it will give you is the line number. So I'm going to assume I spelled something. So, and I spelled something wrong. It's a coupling of dyslexia and poor spelling. Alright, so, but you see, if you don't check for that sort of thing and it'll just go on its merry little way, it won't error out when you try and actually render your scene all the time. It won't be, let's see, what's 16? It won't be obvious, so it's very important. So let's see, vector 4. Actually got a printout over here, so vector color. So vector 3. And I just spotted it. This should be a mat 4. This is a 4x4 matrix, not a vec 3. So that was bad on me. Let's go ahead and stop this. And one more time. Alright, so step. Alright, so now it's jumped over, so now we have a fully compiling fragment, or vertex shader, pardon me. So now we just got to do the exact same thing with the fragment shader. And I'll be honest, I got myself into trouble doing this earlier. One thing you want to be very careful of, what happened, I'll just say, I won't demonstrate this one, but what happened was I just copied this portion, and the fragment shader actually had an error, but when it went to go get the error log, it was getting it for the vertex shader, which the vertex shader was compiling just fine. So I was left dumbfounded because I was like, well, this thing doesn't seem, it won't compile, but it doesn't have an error. So very important there. So we're going to just go ahead and reuse this guy right here, except we're going to point him at the fragment shader. So just a quick once over. So set that guy. That takes the text to the fragment shader. Actually, that's the capital. I should probably use better Hungarian notation there. So that'll set the text. If it doesn't compile, it will fall through here. Okay, so assuming that there's no errors in there, we now have 2 compiled shader programs. So the only thing left, like any C++ program, is to link them. So we got to create a program in the card. So these programs are actually a collection of shaders that we can use with the various types of objects. So we can have multiple shaders per program, and we actually can specify which one we want to use at what time. So you can have like one program whose shaders do Phong shading, another one that does texture mapping. Think of shaders, if anybody's ever worked with OpenGL, or not OpenGL, pardon me, with programs like Blender or 3D Max. The different shaders can like be the different materials that you use. In fact, I was looking at some stuff recently that said that's more than just an analogy. That might actually be the case, such that you can get those programs to write your shaders for you. I can't confirm that yet, but like I said, that seems to that might be the case. Kind of made sense when I heard it. So we're going to go ahead and link our Vertex Shader and our Fragment Shader. And then we are going to actually link the 2 programs. Okay, we've attached them, pardon me. So here's where we call our link. Alright. And missing an R. Alright, so there we go. That's going to go ahead and that's going to compile our Vertex Shader, Fragment Shader. It's going to link it to this program, and that program's name is going to be passed back to our main routine, so we can use that when we actually go to do our rendering. So I'm going to cut this video off here. The last video ran about 50 minutes. So make comments, tell me if I'm doing an okay job, anything you'd like to see or anything you'd like me to do differently, and have a good evening.